My name is Eric Holgerson. I'm the president and project lead. Titan Rover is a multidisciplinary team out of Cal State Fullerton, consisting of over 30 engineering, computer science, and earth science majors. The team is divided into 4 sub-teams: mechanical, robotics, controls, and science. Using the invaluable lessons learned in last year's competition, every single system and subsystem was assessed for its ability to meet all the competition requirements. It is with great pride to present Titan Rover's 2017 platform, Atlas.
This year's chassis consists of welded aluminum, square tubing with structural supports to ensure the chassis remains light and will be able to withstand any worst-case loading scenario in the field. We have ensured the center of gravity will be low enough to account for any steep gradients we might encounter. The length and ride height were also designed and simulated to ensure that the Rover will have the clearance for a half-meter drop with minimal impact load. The suspension is fully independent and comprised of parallel upper and lower control arms in a 4-bar linkage configuration. We have also adopted an inboard suspension system with the shocks attached to the lower control arm and are fully enclosed in the chassis. Air shocks were selected to allow the air spring rate, rebound, and height of the Rover to be adjusted between tasks. We developed our own in-hub wheel and motor assembly to allow the motors to be protected from collisions. Our motor assembly consists of 2 brushed DC motors mounted to a single gearbox, providing a high torque output.
For this year, we are taking a much more centralized approach to the Rover's main control systems. We have opted to use a Raspberry Pi 3 that will act as the brains and central nervous system of the Rover. This single Raspberry Pi will send movement commands to the arm and mobility systems while also receiving critical systems feedback and science data from the science cache. The arm and mobility system will both be controlled via USB joystick. The arm will be using a hybrid 1-to-1 and inverse kinematic solution for a 7 degree of freedom. The Raspberry Pi will also receive data from an onboard inertial measurement and GPS unit. We are able to achieve centimeter accuracy by using real-time kinematics on a dedicated Intel chip, allowing us to map out an accurate path for our autonomous navigation task. Our communication system has also been upgraded by using a point-to-point ubiquity network, which gives us 2 main benefits: high bandwidth at a distance, allowing for video feedback and Rover data to be exchanged without issues, as well as allowing us to operate on a less utilized frequency to prevent interference with other teams.
This year's Robotic Arm is a carbon fiber aluminum hybrid, consisting of 7 degrees of freedom, each with individual feedback. Manufacturing carbon fiber limbs requires a devoted team exclusively for research and development to ensure that it will not fracture under the expected loading conditions. To ensure compatibility and maintainability, a proprietary mount was created. This wristwatch mount provides a universal mating of the joints to the carbon fiber, allowing for alternative attachments such as a science cache device to be installed with ease. The aluminum joints have been shelled and pocketed not only to save weight, but also to provide a safe routing of wires and electronics. The arm is powered by 2 heavy-duty linear actuators and 5 high-torque stepper motors. These actuators provide the capability of lifting a 5-kilogram payload. Many tasks this year require an extremely dexterous arm. For this, we have implemented an unlimited 360-degree rotating wrist that will allow for simplistic execution of any screwing applications that we may encounter in competition. This, paired with our advanced compound gripper, allow for effortless grip on a variety of complex geometry.
This year's science plan focuses on 3 primary science objectives. The first is the collection and storage of a soil sample using the auger bit on our science cache device. This device includes an infrared laser thermometer as well as a soil probe that measures soil moisture and dielectric conductivity. The second component is an environmental analysis, which includes sensors that measure CO2 abundance, background radiation, temperature, humidity, and barometric pressure. These will provide insight into the climate around the field area. The sensors display their readings through our custom user interface, which graphs and stores the incoming data. The third component is our experimental ground-penetrating radar device, which will provide tomographic images of the subsurface. A 440 MHz pulse is transmitted and received through a Baofeng radio, with the data being collected through a USB oscilloscope controlled by a Raspberry Pi. Radio reflection times are then displayed using GPR software to give insight into subterranean structural and hydrological features. We are currently testing different antennas for the best wave propagation that will ensure the deepest penetration depth with minimal systems interference.